हाँ इम्तियाज दिख रहा है। अच्छा नहीं दिख रहा है। ठीक है देखते कर रही हूँ कर रही हूँ। है ठीक है ओके। चलो। Good afternoon, students. Today we'll study tree data structure. So, a tree is a recursive data structure containing the set of one or more data nodes, where one node is designated as the root of the tree, while the remaining nodes are called as the children of the root. Now, as the definition says, it is a recursive data structure. Why we are calling it as recursive data structure? Because whatever can be the length of the tree, the procedure is that we have to consider a root node and then the another node. Like yesterday we had discussed linked list. So in linked list we are having a node. In a node we can either store data, we can store data and addresses or references, you can say. So similarly here also, if we are having one node, so we can insert one node we'll consider as root, and one another node we can insert either at left or we can insert either at right, and we can repeat this process recursively. That's why we are calling it as recursive data structure containing the set of one or more data nodes, where one node is designated as the root of the tree. So this point is important, that one node will be the root of the tree, and while the remaining nodes are called as the children of the root. So the nodes other than the root node are partitioned into the non-empty sets, where each one of them is to be called subtree. So the main node is called as the root node. Now the rest of the tree is partitioned into two parts: left of root node and right of root node. So this partitioned tree is called as subtree. Now nodes of a tree either maintain a parent-child relationship between them or they are sibling nodes. So if the root node is having left node and right node, then the root node will be the parent node and the left and right nodes will be the child nodes. This is one relationship. And the nodes, those who are at the same level, the child nodes, are they can also be called as sibling nodes. In a general tree, a node can have any number of children nodes, but it can have only a single parent. So this is very important, that only one root node will be there and rest of the nodes are called as child nodes. So this is the image which shows a tree where the node A is the root node of the tree, while the other nodes can be seen as the children of root node or children of A. So here we can now we'll see the different terminologies which we are using up till now. So what we have said, that uh, tree data structure is a recursive data structure. So in this, first of all, we are having one root node. Now if next node we want to insert, we can either insert it in left or we can insert it in right of the root node. Now after that, if suppose I've inserted the next node in the left of the root node, now again if I want to insert another node, I can either insert it to the left or I can insert it to the right of that particular node, which node I have inserted right now. So in this way, recursively we can insert nodes. Now this node or the first node of the tree is called as root node or the parent node, and rest of the nodes will be the child nodes. Now the nodes which are at the same level can be called as siblings. Now here in this, if we'll see the subtree, so root node A will have two subtrees, or you can say three subtrees. One which is having B as the node, second C, and third D. So this T1, T2, T3, these are the subtrees of this tree. Now level, we'll study level later on, but this is the image which shows a tree data structure. Now the basic terminologies of tree. So first is the root node. So root node is the topmost node in the tree hierarchy. In other words, the root node is the one which doesn't have any parent. So the first node of the tree will be the root node, and the root node will be the topmost node in the tree hierarchy. So tree is basically for representing hierarchical data. So in the hierarchy, whichever is the first node or the topmost node is called as root node. The root node is the one which doesn't have any parent. Root node is itself the parent, so root node doesn't have any parent. Next is subtree. So if the root node is not null, the tree T1, T2, and T3 is called subtrees of the root node. So in this example, tree T1, tree T2, and tree T3, these are called the subtrees of the tree which is having root node A. Next is leaf node. The node of tree which doesn't have any child node is called leaf node. So here in this example, E, F, C, G, H, these are the leaf nodes. Why these are called as leaf nodes? Because these nodes are not having child. Further, nodes are not there connected to them. So these are called as leaf nodes. Leaf node is the bottommost node of the tree. There can be any number of leaf nodes present in a general tree. Leaf nodes can also be called as external nodes. So now we are having external nodes as well as internal nodes. So in this diagram, A is the root node, B, E, F is one subtree T1, C is one subtree T2, D, G, H is one subtree T3. Now, if we want to see the leaf nodes, so E is the leaf node because it doesn't have any child node. So E, F, C, G, H, these are the leaf nodes. Now these nodes are also called as external nodes. B and D, these nodes are called as internal nodes. So now we are having root node, we are having leaf node, we are having external node and internal node. So root node is the node which is at the topmost, leaf node is the node which is at the bottommost, and leaf nodes doesn't have childs. These leaf nodes are also called as external nodes, and the nodes which are in between the root node and the leaf nodes are called as internal nodes. Path. The sequence of consecutive edges is called path. In the tree shown in the above image, path to the node E is A to B and B to E. So here path is these are the edges which are connecting nodes. So if we want to traverse from A to E, so the path is A to B and B to E. If we want to traverse A to F, so the path is A to B, B to F. Ancestor node. An ancestor of a node is any predecessor node on a path from root to that node. The root node doesn't have any ancestors. Node F has ancestors B and A. The node which is one level above to that node, the node which is connected one level above to the node of which ancestor nodes we are finding out. So if we want to find out the ancestor node of F, so it is B and A. If we want to find ancestor node of E, it is B and A. Now it is important that root node doesn't have ancestor nodes. degree. Degree of a node is equal to number of children a node have. So degree of a node is equal to number of children a node have. So in this diagram, degree of node E is 0 because it doesn't have childs. Degree of B is 1 because, sorry, degree of B is 2 because it is having two childs, 1 plus 1. So degree of B is 1, degree of A is 2 because we are level 2 above. Degree of a node is equal to number of children a node have. In the tree shown in the above image, the degree of node B is 2. Degree of a leaf node is always 0, while in a complete binary tree, degree of each node is equal to 2. So degree of node B is 2 because it is having two childs. Degree of node A is 3 because in this path it is having three childs. Next is level. Each node of the tree is assigned a level number in such a way that each node is present at one level higher than its parent. Root node of the tree is always present at level 0. So level is each number of the tree is each node is present at one level higher than its parent. So here you can see root node is at level 0. So the next nodes which are at the next level will be at level 1. Then the next nodes will be at level 2 and so on. So we have to start from root node, and always root node is having level 0. Similarly with height of leaf nodes are 0. Height of these internal nodes is 1, that is B and D. Height of A is 2. Now, up till now we had discussed general tree. Now we'll discuss binary tree. So binary tree is a special type of generic tree in which each node can have at most two children. In the diagram which is given to us, root node is having three children. So this is not a binary tree. It is a tree, but this is not a binary tree. So in binary tree, it is compulsory that the root node will have two children at most. It can have one children, it can have zero children, at most it can have two children. So binary tree is a special type of generic tree in which each node can have at most two children. So binary tree is generally partitioned into three disjoint subsets. One is the root node, second is the left subtree, and third is the right binary subtree. So left subtree should also be a binary tree, right subtree should also be a binary tree. So in this way, binary tree is partitioned into three disjoint subsets. One is the root node, second is the left subtree, and third is the right subtree. So this is the diagram for binary tree. Here root node A is having two child nodes B and C. Node B is having two child nodes and node C is having two child nodes. So either you can have zero childs, you can have one, or at most you can have two childs. So this tree is called as binary tree. Now types of binary tree. So there are two types of binary tree: strictly binary tree and complete binary tree. So in strictly binary tree, every non-leaf node contains non-empty left and right subtrees. In strictly binary tree, every non-leaf node contain non-empty left and right subtrees. Non-leaf nodes means the intermediate nodes. So every intermediate node contains non-empty left and right subtree. Either we'll have a right subtree or we'll have a left subtree. The degree of every non-leaf node will always be 2. A strictly binary tree with n leaves will have 2 into n minus 1 nodes. So a strictly binary tree with n leaves. So for example, if this is a strictly binary tree, so here we are having four leaf nodes. So if we are having four leaf nodes, then a strictly binary tree will have 2 into 4, that is 8 minus 1, 7 nodes. So in this diagram, you can see we're having 7 nodes. So this is a strictly binary tree. Next is complete binary tree. So a binary tree is said to be a complete binary tree if all of the leaves are located at the same level. Like this is strictly binary tree because every node will have two childs here, or they don't have childs. So this is root node A is having two childs, then this node C is having two childs, node D is having two childs, node B and node E, node F, G, these are not having any child. So either you will have two childs or you won't have any child. So this is strictly binary tree. This is not the complete binary tree, because in complete binary tree all the leaf nodes will be at the same level. Here you can see in a complete binary tree, all the leaf nodes are at the same level. So in this diagram, you can see node D, node E, F, G. These are all leaf nodes and all of them are at same level, that is level 2. So this is complete binary tree, whereas this is strictly binary tree. Now next is the tree traversal. So what exactly traversal is? Traversal is to visit each and every node in your tree at least once. That is called traversal. I'll repeat again. What is traversal? Traversal is visiting each and every node in your tree at least once. That is, you must visit each and every node in your tree. No tree should be left. Now, there are methods for traversing this. So there are three methods for traversing a binary tree: pre-order traversal, in-order traversal, and post-order traversal. So in all these three, pre-order, in-order, and post-order, the root node is important. When we are going to visit the root node. So in pre-order, first we are going to visit the root node, then the left subtree, and then the right subtree. This is the pre-order. In order, first we'll visit the left tree, then or the left node, then the root node, and then the right node. So your root node is in order. So it is left, root, and right. In post order, first we'll visit the left node, then we'll visit the right node, and then the root node. Post, first left, then right, and then the root node. So in all the three orders, pre order, in order, post order, ये जो order है, ये order root को हम कब visit करेंगे ये define करता है. So in pre order, first we are going to visit the root. In post order, we are going to visit the root last, and in order it will be left, root, and then right. So pre-order traversal, traverse the root first, then traverse into the left subtree and right subtree. This procedure will be applied to each subtree of the tree recursively. So we have to repeat this thing. For example, this is the tree. Now we have to traverse this tree. That means we have to visit each and every node of the tree. So for that, if we are using pre-order traversal, so in pre-order traversal, first we'll visit the root node. So root node is A, so first we'll visit A, then we'll go to left subtree. Now in left subtree, again recursively we have to follow the same thing, that is root, left, and right. So now B is the root node. So after A, we'll visit B. After B, we'll visit left of B. So left of B is D and right of B is E. So the sequence will become A, B, D, E. That is root node, then left, then again in left, left node will become the root node. So now again root, left, and right. So the sequence will become A, B, D, E. After that, right subtree. So right subtree is CFG. So again first we'll visit the root node. So that is C, then the left node or the left subtree, and then the right subtree. So the sequence is C, F, G. So the final sequence in pre-order traversal is A, B, D, E, C, F, G. Next is in order traversal. So in order traversal, it traverses the left subtree first, then traverse the root, and then the right subtree. Now again, this procedure is repeated recursively until the whole tree is visited. So first we'll start with left. So the left node is D. After D, we'll visit B because it is left, root, and right. So left node is the D node, then D, B, E. So the sequence is left, root, right. So it is D, B, E. Now again, this is the left subtree. So we have finished with left subtree. Now left subtree, root node, and right subtree. So left subtree is finished. That is D, B, E. After that, root node. So it is A. Now the right subtree. Now in right subtree, again we are having one tree. So left, root, right. So it is F, C, G. So the final sequence is D, B, E, then A, then F, C, G. So this is in order traversal. Now last is post order traversal. Traverse the left subtree and then traverse the right subtree and root respectively. So at last we have to traverse the root. This procedure will be applied to each subtree of the tree recursively. Now again the same tree we'll consider. So first we have to consider the left subtree. So in left subtree again left node, right node, and then root node. So it is D, E, B. Then we'll consider the right subtree. Again in right subtree, left node, right node, and root node. So it is F, G, C. And finally the root node. So the sequence will become D, E, B, F, G, C, and then A. So this is the post order traversal of the binary tree. Now next is the binary tree representation. So there are two representations. One is linked representation and second is sequential representation. So in linked representation, the binary tree is stored in the memory in the form of a linked list. Here in this diagram, you can see the tree is stored in the form of linked list, where the number of nodes are stored at non-contiguous memory locations and linked together by inheriting parent-child relationship like a tree. Every node contains three parts: pointer to the left node, data element, and pointer to the right node. So here in this diagram, you can see root node is A. A is having three parts: one pointer to the left node, one pointer to the right node, and the data element part where we have stored A. Each binary tree has a root pointer which points to the root node of the binary tree. So apart from this, we are having, like in linked list, we are having head pointer. So here in tree, we are having root pointer which is pointing towards the root node of the binary tree. In an empty binary tree, the root pointer will point to null. Now in this figure, a tree is seen as the collection of nodes where each node contains three parts: left pointer, data element, and right pointer. Left pointer stores the address of the left child, while the right pointer stores the address of the right child. The leaf node contains null in its left and right pointers because further they don't have childs, so they don't have to store any address. So the leaf nodes will have null in their left and right pointers. Now in this diagram, we'll see how memory is allocated. So here you can see root pointer is pointing towards 3. So third memory location is basically the root node. So A is the value in the data part, 9 is the left pointer, 7 is the right pointer. So 9, so node 9, that is B. So B is at the left of A. Now this B is having -1 in its left and right pointers because now it won't have further childs. So this is the leaf node, and leaf node will have null in their left and right pointers. The right node of A is 7, that is C. Now C is again having two childs. C's left is D, and at C's right it is E. You can see in this diagram. A, A's left is B. Now B don't have any child, so that's why it is having null in its left and right pointers. A's right is C. C's left is D, and C's right is E. Again, D and E are leaf nodes and they don't have any child, so they'll be having null in their left and right pointers. Next is sequential representation. So in sequential representation, we'll use array. So this is the simplest memory allocation technique to store the tree elements, but it is an inefficient technique since it requires a lot of space to store the tree elements. A binary tree is shown in the following figure along with its memory allocation. So here you can see this is the memory allocation, contiguous memory allocation. So what we have to do is we'll consider that root node A will be we'll store this at location 1, then B at location 2, this is at location 3, 4, 5, 6, 7, 8, 9, 10, 11. So 8, 9, these locations will be empty because now we don't have elements for 8th and ninth location, but for 10th and 11th location we are having elements. So here you can see A, B, C, D, E, F, G, 8th and ninth location are empty, then at 10th location H, and at 11th location I. In this representation, an array is used to store the tree elements. Size of the array will be equal to the number of nodes present in the tree. The root node of the tree will be present at the first index of the array. If a node is stored at ith index, then its left and right children will be stored at 2i and 2i plus 1 location. If the first index of the array, that is tree 1, is 0, it means that the tree is empty. So right now the tree is not empty. So this much is there for binary tree. Now next is binary search tree. So binary search tree can be defined as a class of binary trees in which the nodes are arranged in a specific order. Or this is also called as ordered binary tree. So binary search tree is again a class of binary tree. It is a part of binary tree, and it is also called as binary ordered binary tree. In a binary search tree, the value of all the nodes in the left subtree is less than the value of the root. So we have to follow this order here. The order is value of left subtree will be less than the value of the root node. Similarly, value of all the nodes in the right subtree is greater than or equal to the value of the root. So whatever the value of root node is, left nodes will be less than that and right node will be equal to or greater than that. This rule will be recursively applied to all the left and right subtrees of the root. So this is the binary search tree. So here in this tree, you can see we have to follow the properties of binary tree here, that either we can have two childs or zero childs. This is the property of binary tree. So in binary search tree, we have to follow the property of binary tree plus the order which we have to maintain. So here root node is 30. So all the elements or all the nodes which are at the left part of this root node will be less than 30, and all the elements which are at the right part of the root node will be greater than 30. So in this diagram you can see 15 is less than 30, 7 is less than 15, 22 is greater than 15, 17 is less than 22, and 27 is greater than 22. So we have to follow that ordered set property for the subtrees also. So root node is 30. So all the nodes which are available in the left of 30 will be less than 30, and all the nodes which are in the right subtree will be greater than 30. So here you can see 60, 45, 75, all these three values are greater than 30. So we have to follow this order, strictly this order in binary tree. So your tree will become binary search tree. Now, advantages of using binary search tree. So first example is searching becomes very efficient in a binary search tree. Since the data set is ordered, the data which we are storing is ordered, so searching becomes very efficient. The binary search tree is considered as efficient data structure in compared to arrays and linked list. In searching process, it removes half subtree at every step, because if I want to search 22, so 22 is less than 30, so I'll traverse to left node. I won't visit the right node, so I have left the right tree, because 22 is less than 30, so it is sure that 22 will be at the left part of the tree. It won't be present in the right part of the tree, so I won't traverse or I won't search this part of the tree, so I leave that part. So with this I'm having half tree. Then next node is 15, so 22 is greater than 15, so again I leave the left tree. Now I'll visit in the right tree. Now 22 is equals to 22, so this is the node which I am searching for. So at every step we are leaving half tree. In searching process, it removes half subtree at every step. Searching for an element in a binary search tree takes O of log n time. In worst case, the time it takes to search an element is O of n. So it also speed up the insertion and deletion operations as compared to that in array and linked list. Now next is example. Create the binary search tree using the following data elements. So we have to start with 43 and we have to follow this sequence only. So 43 will become your root node. Now after 43, next element is 10. So since 10 is less than 43, we have to insert it in the left of the tree. Next node is 79. So 79 is greater than 43. We have to insert it in the right part, and so on. So in step 1, 43 is the root node. Now next element is 10. So we have inserted 10 in the left of 43. Then next element is 79. So we have inserted 79 in the right of 43. Next is 90. So 90 is greater than 43, so we'll go to right. 90 is greater than 79, so again we'll insert it in right. Next is 12. So 12 is less than 43, so we'll visit to left node, left subtree. Then 12 is greater than 10, so we'll insert it in right of 10. Next is 54. So 54 is greater than 43, so we'll go to right. 79. 54 is less than 79, so we'll insert it in the left of 79, because it is less than 79. Next is 11. So 11 is less than 43, so we'll go to left subpart. Now 11 is greater than 10, so we'll go to right. 11 is less than 12, so we'll go to left and insert 12 there. Next is 9. 9 is less than 43, so we'll visit 10. 9 is less than 10, so again we'll insert 9 to left of 10. And at last 50. So 50 is greater than 43, so we'll go to right. 50 is less than 79, so we'll go to left. 50 is less than 54, so again we'll go to left and insert the node here. So in this way, the binary search tree is created by maintaining the order. Like every time the root node will be a node which is having all the value lesser than root node in the left subtree, and all the value greater than root node in the right subtree. Now the operations which we can perform on binary search tree, so it is searching, insertion and deletion. So finding the location of some specific element in a binary search tree is called as searching. Insertion means adding a new element to the binary search tree at the appropriate location so that the property of BST do not violate. So whenever we are going to insert or delete values from the binary search tree, we have to follow the properties of the BST. We don't have to violate the properties. Then deletion in BST. So deleting some specific node from a binary search tree. However, there can be various cases in deletion depending upon the number of children the node have. So, but we have to follow the property of the binary search tree. We have to maintain the order of the binary search tree. Next is the AVL tree. Now, all these trees are binary trees only, but with certain properties. So, next is AVL tree. So, AVL tree is invented by GM Edelson, Welsky, and EM Landis in 1962. So the tree is named AVL in honor of its inventors. So that's why it is called as AVL. Otherwise, it is a binary tree only, or binary search tree, you can say. So AVL tree can be defined as height balanced binary search tree. This is important. AVL tree can be defined as height balanced binary search tree in which each node is associated with a balance factor which is calculated by subtracting the height of its right subtree from that of its left subtree. So AVL tree can be defined as height balanced binary search tree. So here we have to balance the height of the binary search tree. In normal binary search tree, we don't have to balance the height of the tree. Tree can be a skewed tree, but it should follow the property of binary tree, plus it should be ordered, then it is called as binary search tree. But AVL tree is basically a height balanced binary search tree. So here we have to balance the height. Now for that we have to calculate the balance factor for each and every node. Now how to calculate balance factor for each and every node? So the height of its right subtree, balance factor is calculated by subtracting the height of its right subtree from that of its left subtree. Mhm. This is the AVL tree. So we have to calculate the balance factor at every node. So balance factor of 25 is 0. Why? Because it don't have left subtree or right subtree. So 0 minus 0 will give you 0. Now we have to calculate balance factor for 50. So left subtree is 1. It is having one child. Whereas in right subtree it is having two childs. So it is left child, number of left child minus number of right child. So number of left child is 1 and number of right child is 2. So 1 minus 2 is minus 1. So this is the balance factor for node 50. Now if we'll calculate balance factor for node 100, so it is having three childs, 50, 75, 85. So it is having three childs. So the left tree is 3 and the right tree is having two childs, 150, 125, or 150, 175. So it is having two childs. So it is 3 minus 2 will give you 1. So in this way we have to calculate balance factor for each and every node. So here balance factor which is calculated by subtracting the height of its right subtree from that of its left subtree. Now tree is said to be balanced if balance factor of each node is in between -1, 0 or 1. Otherwise the tree will be unbalanced and need to be balanced. So we have to, in AVL tree it is a binary search tree, but we have to balance the height. Now how to balance the height? For each and every node we have to calculate the balance factor. How to calculate balance factor? Height of left subtree minus height of right subtree will give you the balance factor. Now the balance factor should be in between -1 to 1. This means we can have three values for balance factor: -1, 0 and 1. If the balance factor is between these three ranges, -1, 0 or 1, then we can say the tree is balanced. Otherwise the tree is unbalanced and we have to balance this tree and it needs to be balanced. So balance factor, how to calculate balance factor? It is height of left subtree minus height of right subtree. If balance factor of any node is 1, it means that the left subtree is one level higher than the right subtree. If balance factor of any node is 0, it means that the left subtree and right subtree contain equal height. If balance factor of any node is minus 1, it means that the left subtree is one level lower than the right subtree. So balance factor 1, 0 and minus 1 is allowed. So this is the AVL tree, because in whole tree for every node we have calculated the balance factor, and balance factor is in the range minus 1, 0 and 1. So this tree is called as AVL tree. Now operations on AVL tree. Now, since it is a fact that AVL tree is also a binary search tree, therefore all the operations are performed in the same way as they are performed in a binary search tree. So here we can do searching, here we can do insertion, here we can do deletion. Only the point is, while doing insertion and deletion, we have to calculate the balance factor for that particular node, and we have to see that if the tree is balanced or not. If the balance factor is other than minus 1, 0 or 1, then we have to balance the tree. So that balancing the tree is again one step. So we'll study those steps later on. Searching and traversing do not lead to the violation in property of AVL tree. Simply we have to visit the tree. So searching and traversing, it does not violates the property of AVL tree. However, insertion and deletion are the operations which can violate this property, and therefore they need to be revisited. So if we have inserted any node, and if it violates the property of AVL tree, then we have to make changes, or we have to balance the tree. So how this balancing is done? So this balancing is done using rotations. So here insertion in AVL tree is performed in the same way as it is performed in a binary search tree. However, it may lead to violation in the AVL tree property, and therefore the tree may need balancing. So the tree can be balanced by applying rotations. So we'll study these rotations later on. Now deletion can also be performed in the same way as it is performed in a binary search tree, but deletion may also disturb the balance of the tree. Therefore, various types of rotations are used to rebalance the tree. So we have to, while inserting and deleting elements from AVL tree, we have to see the balance factor. And if the tree is balanced, there's no problem. And if the tree is unbalanced, then we have to perform several rotations. Then the tree will become balanced. Now, why AVL tree? Why not the binary search tree? So AVL tree controls the height of the binary search tree by not letting it to be skewed. So that's why we are using binary search tree. AVL tree. The time taken for all operations in a binary search tree of height h is O of h. However, it can be extended to O of n if the BST becomes skewed. That is the worst case. By limiting this height to log n, AVL tree imposes an upper bound on each operation to be O of log n, where n is the number of nodes. So here you can see that it is reduced by half. Now, next is AVL rotations. So we perform rotation in AVL tree only in case if balance factor is other than minus 1, 0 and 1. Now there are four types of rotations which are as follows. LL rotation, RR rotation, LR rotation and RL rotation. So LL rotation is basically left rotation. Here the tree becomes imbalanced because of this. So a node is inserted in the left subtree of A. A is, for example, the node whose balance factor is other than -1, 0, or 1. So we have to balance the balance factor of node A. So how it is changed? It is changed by inserting a node in the left subtree of A. That is LL rotation. Then next is RR rotation. Inserted node is in the right subtree of A. LR notation is left right. So inserted node is in the right subtree of left subtree of A. And RL rotation, inserted node is in the left subtree of right subtree of A. Now we'll see the rotations one by one. So the first rotation is RR rotation. The first two rotations, LL and RR, are single rotations, and the next two rotations, LR and RL, are double rotations. For a tree to be unbalanced, minimum height must be at least 2. Now we'll see each rotation. So the first rotation is the RR rotation. When BST becomes unbalanced, binary search tree becomes unbalanced due to a node is inserted into the right subtree of the right subtree of A. Here you can see this is the node A. A node is inserted in the right subtree of right subtree. Node C is inserted in right of the right subtree, that is B. So this is RR. So here you can say that this is in the right and this is also in the right. Because of this, the balance factor of A is other than -1, 0, and 1. So balance factor of A is -2 basically. So because we have to subtract height of left subtree with height of right subtree. So height of left subtree is 0. 0 minus 2 will give you -2. So height of A is, or balance factor of A is -2, which is other than -1, 0, and 1. So we have to perform the rotation. So in RR rotation, we have to perform a single rotation anti-clockwise. Here you can see we have to perform a single rotation anti-clockwise. So in this single rotation, what we had done, we had rotate B. So B becomes the root node, A becomes the left node, and C becomes the right node. Now at this time you can see the balance factor. So balance factor is 0, 0, 0, which is allowed. So here the tree is skewed at right. So the balance factor of A becomes 2. So this is not the height balanced binary search tree. So we have to balance the height. So for balancing, we have to perform the rotation. So in RR, we have to perform the left rotation. So we had rotated it in anti-clockwise direction. So node B becomes the root node, node A is in the left, and node C is already in the right. Next is the LL rotation. This happens because a left subtree is inserted to the left subtree of the node C. So that's why the balance of C changes. So it is 2 because the height of node C is 2 and height of right subtree is 0. So 2 minus 0 is 2. So we have to balance this. Now for balancing this, again we have to perform rotation. So this rotation is in clockwise direction. So again, B will become the root node, C will be at the right of it, and A will be at the left of it. And now if you will calculate the balance, you will see balance factor, you will see it is 0, 0, 0, which is allowed. So your tree is balanced. Now LR and RL rotations. So in LR and RL rotations, two rotations we have to perform. So for example, why it is called as LR notation? Because the balance of the tree changes because the node is inserted to the left and then to the right. Because of this, balance of this node is changing. So that's why it is called as LR, left and then right. So a node B has been inserted into the right subtree of A, the left subtree of C. So it is left and right. That's why the rotation is called as LR. Because of which C has become an unbalanced node having balance factor 2. This case is LR rotation where inserted node is in the right subtree of left subtree of C. As LR rotation is RR plus LL rotation, hence RR on subtree rooted at A is performed first. By doing RR rotation, node A has become the left subtree of B. So here at this point, here in LR or RL rotation, we have to perform two rotations. So the first rotation is R. We have to make the tree from LR to RR. Sorry, from LR to LL, left left. So we have to bring all the nodes in left. So what we'll do one anti-clockwise rotation. So B will come at this position. So it is C B A. Here you can see it is C B A. Still the balance factor of C is not proper. So again we'll perform here one clockwise rotation. So this clockwise rotation will bring B to root node, then A to left and C to right. So here you can see B will become the root node, A will be at the left and C will be at the right. Now the balance factor is 0, which is in the range -1, 0 or 1. So now the tree is balanced. So this is LR notation. Now the next rotation is RL rotation. So imbalance occurred because of insertion at right and then insertion at left. So you can see balance factor changes here at A. Why? Because one node is inserted at right and another node is inserted at left. That's why it is called as RL. So what we'll do, we'll perform one rotation here. This RL, we'll make it RR. So we'll first skew it. So for doing that, we have to perform one clockwise rotation. So we'll bring B here and then C will be to the right of it. So here you can see A, B, C. Now again, the balance factor is not proper. So for maintaining the balance factor, now we have to perform one left rotation, which is anti-clockwise. So now for this anti-clockwise rotation, B will become the root node, A will be at the left and C will be at the right. So here you can see in this diagram, now the tree is balanced because balance factor is 0. So in this way, the rotations are performed. So in LR rotation and RL rotation, two rotations are there, whereas in LL rotation and RR rotation, only one rotation is there. Now next is construct an AVL tree having the following elements. So first we'll insert the node H. So balance factor of H is 0. That's okay. Then we'll insert I. So I will come after H. In the sequence of A, B, C, D, I will come after H. So I is bigger than H. So we'll insert I in the right of H. Now again balance factor of H is -1 because 0 minus 1 will give you -1. So balance factor of H is -1. It's okay. There's no problem. Then the next element is J. Now J is greater than H is greater than I. So we'll insert it here. Now balance factor of J is 0. Balance factor of I is -1. Whereas balance factor of H is -2. So here we have to adjust or balance this tree for H, and how this balance gets changed by inserting RR. Here I is inserted at right and J is also inserted at right. So it is RR. So we have to perform this RR rotation and we have to rotate it anti-clockwise. So while rotating it anti-clockwise, I will become the root node, H will be at the left of I and J will be at the right of I. Here you can see now the tree is balanced. I will become the root node after performing the rotation. I will become the root node, H is at the left and J is at the right. Balance factor of all the three nodes is 0 and which is in the range. So the tree is balanced. Now next we have to insert B. So B is less than I, B is less than H. So we'll insert B here at the left. Here you can see we have inserted B. Now while inserting B, again we have to calculate the balance factor. So balance factor of B is 0, balance factor of H is 1, balance factor of I is 1, balance factor of J is 0. So all the balance factors are in the range -1, 0 and 1. So there's no problem here. Then we have to insert A. A is less than I, we'll go to left. A is less than H, we'll go to left. A is less than B, again we'll go to left. Now because of this insertion, balance factor of H changes. Now it becomes 2. So we have to manage this. So while doing this, this is LL because B is at left of H and A is of left of B. So it is LL. So we have to perform one clockwise rotation. While performing this clockwise rotation, B will come up, A will become the left child and H will become the right child. Here you can see B will come up, A will become the left child and H will become the right child. Again, we have to calculate the balance factors and we have to see that the tree is balanced. Now next we have to insert E. Now E is less than I, E is greater than B, E is less than H. So we'll insert here. We'll insert E to the left of H. Now the balance factor of 2 is getting changed because of left right. So this is LR rotation. So in LR rotation, first we have to make it LL. So H will come to B, place of B. Here you can see H will come to place of B and B will come here and then AE. Now then we have to perform the second rotation. So in the second rotation, B will come to the root node and H will go to the right of it. Sorry, H will become the root node, B will come to the left of it and I will come to the right of it. And then again we have to calculate the balance factor and now we can see the tree is balanced. So in this way we can insert the elements in the avial tree by balancing its height. So this is called as height balanced binary search tree or it is called as avial tree. So while inserting or deleting, every time whenever we are going to do the insertion or deletion operation, we have to calculate the balance factor. And with the help of that balance factor, we have to see whether the tree is balanced or not. And if the tree is imbalanced, so we have to balance it by making rotations. So in this way, the tree is created here. Now next is B tree. So in next lecture, we'll discuss B tree. Or we can see the definitions of B tree. So B tree is a specialized M-way tree that can be widely used for disk access. So it is a specialized M-way tree, means we can have multiple nodes here. We don't have to follow the property of binary tree here. A B tree of order M can have at most one M minus 1 keys and M children. So we have to see the order. If order is M, this means we can have M minus 1 keys and M children. One of the main reason of using B tree is its capability to store large number of keys in a single node and large key values by keeping the height of the tree relatively small. So for searching, this B tree is very efficient or for storing data in a disk. Here accessing of data becomes very fast if we are going to store the data in the format of B tree. A B tree of order M contains all the properties of an M-way tree. In addition, it contains the following properties. Every node in a B tree contains at most M children. Every node in a B tree except the root node and the leaf node contain at least M by 2 children, and the root nodes must have at least 2 nodes. All leaf nodes must be at the same level. So height of the tree will be mostly 2 or 3. That's it. So here we can restrict the height of the tree, so searching becomes fast. So here you can see this is the B tree. This is the root node. This root node must have two nodes, two child nodes. So here you can see the root node is having two child nodes. Now these two child nodes can have any number of leaf nodes, and only this much will be the height of the tree. If we want to insert, we can insert the values here. Here you can see the values are in sequence: 10, 23, then 29, 30, 31, 32, so 60. So all the value which is less than 60 is in the left of the tree, all the value which is greater than 60 is in the right of the B tree. So in next lecture, we'll discuss the various operations which we can perform on B tree. Then we'll discuss B plus tree, and then the problems which are asked in GATE on the topic tree. So this much we'll discuss in next lecture. Thank you.